next we're going to discuss something called symmetries, and we'll describe what we mean by symmetries in a moment. But here we're going to talk about first symmetries of a rectangle. On the worksheet and on the homework, you'll also work with a square and an equilateral triangle. Maybe even a scalene triangle, which has none. But let's first talk about a rectangle, and we'll use this to illustrate what we mean by symmetries. We're going to take a rectangle, and I'm going to number the corners. I'm going to number them like this, because this is how I wrote it in my notes. So we're going to take this rectangle, and we're going to find symmetries, meaning we're going to apply we're going to move this rectangle around, and a symmetry will be when the resulting rectangle after the move is still in this same shape. So in particular, if you do something, you rotate it 90 degrees, say. You rotate it 90 degrees, you rotate this 90 degrees, it'll look like that. And that will not be a symmetry. But what symmetries do exist? Well, we're going to talk about, there are two different kinds of symmetries. First, we have rotational symmetries. And rotational symmetries are described like I just described. We rotate it by an angle. So we saw that rotating at 90 degrees didn't work. But there are two rotational symmetries. First, we're going to assume a clockwise. For all of these, we'll assume clockwise rotation. You could do a parallel counterclockwise argument. Rotational symmetries, clockwise. How can we rotate this and result in the same rectangle? Well, first, we can rotate it 0 degrees. Debating how I want to organize all of this. I'd like all of them to be on the same board. Okay. So I'm going to put this as a bullet. First bullet. We can rotate it 0 degrees. You rotate it 0 degrees, what do you get? You get the rectangle. You get that exact rectangle. That will be a symmetry because we applied a rotation. We rotated at 0 degrees, and we have the same rectangle. In particular, the same shape. What else can we do? Well, we saw before, if you rotated 90 degrees, you start with this paper. I hope paper shows up on the camera. And you go like this. That's going to be a different shape. But you could go halfway around. Meaning you could rotate it 180 degrees. And what do you get if you rotate 180 degrees? Well, you get that shape, but again, we're going to keep careful track of our corner points. So you rotate this 180 degrees, this 1 now goes down here. You rotate 180 degrees, the 2 goes up here, the 3 goes here, the 4 goes there. Are there any other rotational symmetries? Well, 207, so here's 0 degrees. Maybe if I use this eraser, it'll be more illustrative. Because an eraser, you're more likely to see. Do I have a book or something? I have a book somewhere. Let's use lots of good books over here I could use. I should use one that kind of applies to what we're doing. Probably shouldn't spend this long finding a good book. Where's this one? There we go. Here, let's just take this book. This applies. The Smithsonian Guides to Natural America, the Mid-Atlantic States, New York, Pennsylvania, New Jersey. That covers probably over half the class. The Delaware Water Gap. Philadelphia. So here, start with a rectangle, rotate it 0 degrees, same shape. Just keep rotating this. None of these rotations are the same shape. So meaning, start at 0 degrees, anywhere between 0 and 90 degrees, you don't get the same shape. The only time you get the same shape is if you go all the way around halfway. That gets you the same shape. You could get the same shape then if you rotate all the way around 360 degrees, but notice if you do that, you get the same symmetry as you do if you don't rotate it at all. So here, we don't have any other rotational symmetries. Any other distinct rotational symmetries. Well, here's another type of symmetry we can talk about. An axial symmetry. An axial symmetry. What does that mean? Well, it's a symmetry that we can describe by flipping around somehow. And I'm going to illustrate these by taking our original one. Maybe I'll put bullet points here also so that they're bulleted like we did over here. Bullet point. Axial symmetry. Start with the original rectangle. Can we flip this around so that we get the same rectangle, the same shape, where the corners are labeled possibly differently? Well, you flip it around that center axis, what happens? You flip it around like that, you get the same shape. So that does work. And how do the corners change? 4, 3, 1, 2. So there's one axial symmetry. Is there another? Yes, there is. 1, 2, 4, 3. So we flipped across a center axis. We could also flip it like this. That gives us the same shape. Why am I not using my book? Let's use this book. The Smithsonian Guides to Natural America, Southern New England, Massachusetts, Connecticut, Rhode Island. That probably covers another quarter of you. So we take, for this first one, we flipped it like this. That gave us the same shape. This next one, we're going to flip it like this. And that gives us the same shape. We're going to flip it across a center axis. And what does that give us? Well, it gives us the same shape, but the numbers are now like this. 1, 2, 3, 4. And are there other axial symmetries? Well, you might think you can do a diagonal type argument, like this. But what happens if you flip it across? Well, that worked out really well with the book. I wasn't sure it was going to work out that well. What happens if you flip this rectangle? Let's use another book. The Smithsonian Guides to Natural America, Northern New England, Vermont, New Hampshire, Maine. What happens if you flip across this diagonal axis? That's not the same shape. We start with this rectangle like that. You flip across that axis, it now goes up like that. So that will not be a symmetry of a rectangle. And any other axial symmetry you could try, you try, like another diagonal type thing, it's not going to work. So here we have only these 4 symmetries. So as a conclusion, I'll just say we have these 4 symmetries of a rectangle. We have these symmetries. One thing I'd like you to notice is in the symmetries in these 4 rectangles, notice that the number arrangements on the sides are not the same for any two of them. That's not a coincidence. So in this first one, we have 1, 2, 3, 4 like this. In this one, this same side up here is 3. In this one, that same side is 4. In this one, that same side is 2. That is not a coincidence. But I'd also like you to observe one other thing. Well, 4 other things. Observe these symmetries have the following properties. Exhibit the following properties. Observe these symmetries exhibit the following properties. 1. Combination of symmetries is a symmetry. What does that mean? Well, it means if you start with your original rectangle, you apply one of these 4, so you rotate it 180 degrees, say, and then you apply a second of the 4. So if you do a rotation by 180 and then flip across this, that is going to give you one of these symmetries. Which one will it give you? Well, in that case, if you rotate 180, if you start with the original, which happens to be here, you rotate 180, you get here, and then you flip across, say, this center axis. Is that also a symmetry? Well, yes, it is, because if you do that, you get this one up here. So, doing 180 degrees and then this second axial flip is the same, as far as the rectangle is concerned, as doing that first one. And you can do that with any 2 of these 4. You know, do the combination of any 2 symmetries, and it will be another symmetry. 2. There is a null symmetry. What do we mean null? A null symmetry being one where it doesn't change the rectangle. Here, our 0 degree rotation functions as our null symmetry. 3. Maybe a little less clear. But there is, for each of these 4 symmetries, there is an opposite symmetry. What do we mean, opposite symmetry? Well, what does that mean, an opposite symmetry? An opposite symmetry means, let's take this 180 degree one, for example. If you start with your rectangle, you rotate 180 degrees, there is another symmetry which undoes that. Meaning there is another symmetry you can then apply which gets you back to the original. So you start with, let's see, I have every book here, so I don't know where you're from. What's next most likely that you'll be from? This one? The far west, California, Nevada. Some of you might be from California or Nevada. So what do we want to do? We want to find an opposite symmetry to 180 degrees. Meaning, we want to rotate 180 degrees, then apply another symmetry which gets us back here. Well, rotate 180 degrees. Now you're here. What can you do to get back? Well, you do one of these flips, it doesn't get you back. You do 0 degrees, it doesn't get you back. But notice, if you do another 180 degrees, it gets you back. So this 180 degrees has an opposite symmetry. Itself is actually the opposite symmetry. And that works for these 2. For 0 degrees, start here, apply 0 degrees, you have that. Apply it again, and you're back to the original. I mean, nothing changed because it's a null symmetry, but it does function as its own opposite. And similarly for these flips, start here, do a flip, well, you're here now, do that same flip, and you're back to the original. If you did this first flip, and then this second flip, you're not back to the original. That changes things around. That actually, I believe, is a 180-degree rotation. Yes, it is. But if we start here, apply this flip, and then apply it again, we're back to the original. And similarly, down here. So all of these symmetries do have an opposite symmetry. Where did I put my marker? Oh, it's in my pocket. I didn't feel it the first time. A fourth property these all share is something called, well, they share associativity. And associative is just like multiplication being associative. You could, you know, with, well, I guess I wrote addition. Addition is associative, meaning if you do 3, you can do the first 2 or the second 2 and get the same thing. That applies also to these symmetries. For this example, I'm not going to be too concerned with showing that that's true, but I'll just tell you that they are associative, meaning if you do 3 symmetries, you can do the first 2 first or the second 2 first. Now, this is all great. We have these symmetries for shapes, and we could do similar arguments for other shapes. But these 4 properties over here don't necessarily have to apply to shapes. These 4 properties apply to numbers as well. These 4 properties apply to numbers as well. Numbers with an operation. So we started with shapes and symmetries, which functioned as operations. But we're going to do this next example. Example. These properties apply to some sets of numbers with some operations as well. So these they apply to some sets of numbers. In the worksheet or the homework, we will have one where something doesn't apply. These properties apply to some sets of numbers with some operations as well. Let's do real numbers with addition. Real numbers with addition. A shorthand notation for that would be an R like that with an extra bar, comma, plus sign. And you could put these in parentheses or like brackets or something. I'm just going to leave it R with plus like that. Now, how do these apply? How do those 4, well, how does this set, so maybe I'll say take the real numbers with multiplication. How does this set of numbers with that operation exhibit these 4? Well, for one, combination of symmetries is a symmetry. Well, for number 1, real number plus real number. If you take a real number, like 6, and add, no, let's choose 7. I like prime numbers. A real number, 7, and add another real number, pi. What do you get? You get 7 plus pi. That's another real number. Real number plus real number is real number. Number 1 applies. Combination, meaning using our operation. In the first example, the operation was one of the 4 symmetries. Well, the operation was applying a symmetry, I should say. So 0 degrees was an operation, 180 degrees, flip, flip were the operations there. Real number plus real number is real number. Null symmetry. Well, what was a null symmetry? A null symmetry was something that you did which didn't change anything. So you started with a rectangle, you applied a null symmetry, nothing changed. Well, is there something, our operation here is addition, is there something you can add to a real number which gives you the same real number you started with? Yes. 0. 0 is within this set. 0 is a real number. So here, in number 2, 0 functions as our null symmetry. Adding 0 functions as our null symmetry. So I'm just going to say here, 0, adding 0 gives the null symmetry. Adding 0 gives the null symmetry. Well, in opposite symmetry, when we were talking about rectangles, the opposite was something that got us back to the null symmetry. So you rotated 180 degrees, you rotated another 180 degrees, you got back to the original. So here what we need is real number. Our operation is addition. Maybe I'll underline what we're looking for. So we want real number plus something else, which gets us back to our null symmetry. So we want real number plus something to give us 0. Well, what can we do there? Well, we can take the negative real number. The negative real number is in that set. So, well, maybe I'll say here, negative real number functions, or maybe I'll say gives, the opposite symmetry. And in 4, associative, again, as I said before, real number plus other real number. I should put check marks after we're done with these. Check marks. Real number and addition is associative, well, are associative. Addition is associative across the real numbers. So right here, real numbers plus addition, or real numbers together with addition, and rectangle with symmetries gave us actually the same 4 properties. And in math, a set with an operation which exhibits those same 4 properties is a very important construct in algebra. It's a very important algebraic construct. It's technically a rather advanced thing in math, something you study in an abstract algebra course. But let's define that. Groups. A group is a collection of objects G together with an operation called star, which we'll call star, such that those 4 properties from before are satisfied. And here we formalize what those 4 properties are using elements of the group and the operation. So closure. The first one we call closure. A star B, A operating on B, is in the group for any A and B in the group. So now you could do this with the symmetries of a rectangle. You know, you do any 2 symmetries together and you have another symmetry. It may be easier to see with our second example, real numbers with addition. So in the second example we did for closure, real number plus real number did give us another real number. And you can do that for any 2 real numbers. Number 2, the second property, the null symmetry, we call the identity. And a group must have an identity element. There's an element I such that A, this should say at the end, for any A in G. Identity. There is an element I in G with A star. Jeez. I hope nobody wrote that yet, but I wouldn't bet on it. There's an element, sorry, that second one should have been the same thing but opposite. There's an element I in G with A star I equal I star A. This just means you can multiply, you can operate in whichever order you want. A star I equal I star A gets us back to A for any A in G. So in the first example, our 0-degree rotation brought us from A back to itself. From A back to itself. Here, we need an element where operating on it doesn't change it. The identity is very important, and frequently if you have a set that is not a group, a set with an operation that is not a group, it won't have an identity element. Well, it may not have an identity element. That's a common way for a set to not be a group. So here, we need A star I to equal I star A, getting us back to A. So in the null symmetry brought us from A to A, the 0-degree rotation. In the second example, real numbers with addition, adding 0 didn't change anything. So in the second example, I was 0 with that operation, the operation of addition. Inverses. So the opposite symmetry we call inverses. For any A in G, so an inverse must exist for any element in the group. For any A in G, there is an element A inverse in G with A operating on A inverse, being the same as doing that backwards, getting us back to the identity. So for any element, we could get back to the identity. So in the rectangles example, you rotate 180 degrees. You do that again, you get back to the null symmetry, the 0-degree rotation. For the second example, the inverse element, a negative of a real number gave us our inverse element, because real number plus its negative brought us back to 0. The inverse gets you back to the identity. So if you're determining whether something is a group, first, well, yeah, I would always do the identity first. First, I would find the identity, if it exists, and then I would try to find the inverses for all elements. So an inverse is an element which gets you back to the identity. And finally, associativity. There's the standard associativity condition. For real numbers with addition, you can add in whatever order you want there. In general, if I ask you to verify associativity, I wouldn't ask you for like the entire set, maybe just for a couple elements in the set. So we saw that, so I'll just say example, both previous examples gave us groups. Well, were groups, I should say. Were groups. The real numbers with addition and the symmetries of a rectangle. Let's look at one more, and then we'll look at one that isn't. So question, does the real, maybe I should say does the real numbers, the positive real numbers I should say, maybe, so I guess I should write that out as a word since we don't have the notation for that. So do positive real numbers with multiplication define a group. So do the positive real numbers. So real numbers, positive, not including 0, with multiplication define a group? Well, let's check our properties. I guess I call them A, B, C, D, so I should call them A, B, C, D. Closed. Is positive real number times positive real number another positive real number? I'll just say yes. Positive number times positive, it's too many words. Number is another, I'm just going to say yes. Positive real number times positive real number is another positive real number. B. Is there an element we can, in this case, multiply by that gets us back to the original element? So we need a number times something giving us itself. Is there a number you can multiply by that doesn't change anything? There is. 1. So with addition, the identity element was 0 because you add 0 and nothing changes. But here, with multiplication, the identity element is 1 because you can multiply by 1 and nothing changes. C. Are there inverses? Well, what is an inverse? An inverse is something you multiply by that gets you back to 1. So given a positive number, is there a number you can multiply? Is there another positive number you can multiply that gets you back to 1? So what if you take 10, for example? 10 times what equals 1? 10 times what equals 1? 10 times 1/10 equals 1. 10 has an inverse. How do you find the inverse? So I'll say yes. A times 1 over A gets us back to the identity. And you can do 1 over A times A and so on. That also works with like numbers like a half. A half times 1 over a half times 2 does get you back to 1. So the inverse does exist for all elements. 1 over A is another real number. 1 over A inverse has to be there. And from here you can see in this example why we use that inverse notation to the -1. It's for something like this. And D, is it associative? Well, I'm just going to say yes. And because of that, the real numbers together with multiplication does define a group. So we have now 3 different things which define a group. How about one that doesn't? Let's see, which one am I going to put on the worksheet? Let's do, how about, yeah, okay, positive real numbers with, so example, addition. So I'm just going to say show the positive real numbers with addition is not a group. So why is it not a group? Well, one of those 4 must not have been true, must not be true. Well, I'll tell you right now, positive real numbers with addition, A is true, and D is true. What about B? Is there an element which you can add that gets you back to the original element? Well, there is such a number, 0. But we're looking at only the positive real numbers. So I'll say this set does not have an identity element, since in this case 0 is not a positive real number. So part B, identity, this set does not have an identity because 0 is not 0 would function as the identity, because you can add 0 to anything and it doesn't change. But 0 is not in the set, so this set does not have an identity. Since it doesn't satisfy part B, it is not a group. So group theory is a very large field in math. But I would like you to try the examples on the worksheet before I go over them on Thursday. I would like you to try to get used to some of these words and how they work. I would consider this far and above the most complicated thing we are covering this semester. But I would like you to try it, see what happens. Also try to be sure you can relate these back to the rectangle symmetries, because it's always nice to have a nice visual for something you're doing.